Hello everyone, I am Yogesh, and today in this episode we shall be continuing from our discussion that we left in our previous episode. If you remember, in our previous episode we discussed about that what will be the electrostatic potential, or in short the electric potential of a single charge, and how will a dipole will behave for if I brought some test charge in its vicinity. Then we saw a very peculiar thing. We saw that if I am considering a single charge, so the dependence of the potential is 1 by r. But in the case of a dipole, the dependence of the potential was 1 by r square. And we also gave the reason that why is that all happening. But since you know, in our previous discussions from the episodes of electrostatics, we all know that it is not always that I can find some discrete charges. I must also take into consideration a situation where there is not only a single charge, but there is a group of charge. And whenever there is a group of charge, and if I am brought in contact or in the vicinity a very simpler or a very smaller test charge, then all those charges will impart their force over them. Suppose if some of them are positive and some of them are negative, and if a single positive test charge is brought in near to them, what will happen? Some of them will repel it, some of them will attract it, and this will go on. So how to find out the electric potential due to a system of charges? Well, actually that is quite simple. Do you remember what we did for the to find out the force of so many charges that they were impelling on a single charge, and also the electric field due to a system of charges? Well, that is the same case here. What we have to do is we have to find out the potential at our point of interest due to a single charge, and then what we will do is, using the superposition principle, we will simply integrate it to all charges. Well, actually it is not integrating, it is we have got if I know that how many charges are there, so suppose 10 or 5, I will simply add them up. But just imagine if there are thousands and millions and trillions of charges and you don't know how many charges are there, then we will use the technique that we used in the continuous charge distribution, considering a discrete one and then integrating it all over the space. Well, this is how we can solve the riddle that what will be the potential due to a system of charges, and that comes out to be inversely proportional to the distance, that is r. That is, v is dependent upon 1 by r, because 1 by 4 pi epsilon naught is a constant, and q is the charge that is repelling my test charge. This case is solved hereby. But just tell me, how will you feel if you have given access to a place where without spending any energy you can move from one point to another? Or let me give you a very good example. Suppose you wanted to go for a ride in a city, and when you go for the bus pass, the ticket man will simply say that sir, here is your pass, you have to pay 100 rupees, and with this pass you can go to each and every place where the transport is available to you free of cost. Well, that means after having that pass, you are not required to pay any more fee in the transport. And so even if you are going to a point A, which is at one end of the city, to the point B, which is the center of it, or to the point C, which is the other end of the city, you are free to do anything and you are free to go anywhere without paying anything extra. Well, in the case of electrostatics, as I told you, that it is not about a pass, but is something like a pass. See, if you want to travel in a transport, what you will have to give? Yes, you will have to give some money. That is the currency out there. But what happens to the electric charges? What do they will have to spend? Yes, exactly. They will have to spend some energy. That is, their potential will be spent. But just like in my case, where I got a pass to go anywhere, the charges also have a freedom in a certain qualitative or a certain dimensions of space. That is, they will have a surface where they can roam quite easily without spending any extra energy, and that surface is known as the equipotential surfaces. Let me break this terminology into two. Equipotential. Equi means equal, potential means the energy that is required to bring a charge from a point A to a point B, or even from infinity to a point B. Then what exactly is an equipotential surface? An equipotential surface is actually a surface where if I put a charge, say a test charge, it has got the freedom to go anywhere it wants without spending any particular potential. Just imagine if you have got some slices of bread and there is an ant over there, and what that ant is having is that that ant is given a freedom to eat as much as bread as it can, but the condition is that for the first bread she is free to do anything, but in order to move from the first bread to the second bread she will have to make a jump, right? That is, she will have to spend some energy. So after finishing everything from the first bread, she will jump to the second bread, and in that process she will be spending some energy. Okay, please don't be angry with me. I will give you your example of interest. Okay, so suppose you are in a building and right now you are on the ground floor. You wanted to go upwards, that is, say suppose you want to meet me and I am on the 4th floor. So if you are feeling a bit lazy and you don't want to spend some energy, what will you do? You will simply call me up and say, Yogesh, I am not coming upstairs, you can come downstairs if you want. And I will say, no, you don't come right now, you take some rest. Now you take some rest and you think that, okay, let me roam around in the corridor. So when you are roaming around in the corridor, you will feel like you're not spending enough energy to do so. But if I give you instructions to come right now on the 4th floor, what you will have to do? You will have to go from the 1st floor to the 2nd floor by using stairs or even lift also. So what you are doing is you are spending some energy from coming from the ground floor to the 1st floor while using stairs, then from the 2nd floor to the 3rd floor, and then finally reaching me. And you will say that while I was on the ground floor I was quite happy, but since you made me to climb up these stairs to come on the 4th floor, I am a bit tired. Well, actually this is the same case that the charges faces whenever they are on an equipotential surface. Just like the floors that we have in a building, they have the equipotential layers. So from layer A to B to C, they will have to spend some amount of the potential. Right now we are going to discuss that what will be the potential that they will spend whenever they wanted to make a transition from one layer of the equipotential surface to the second layer of the same surface, that is an equipotential surface to an equipotential surface. So now since we have discussed that what exactly is an equipotential surface, and we have also drawn some analogy, that is equipotential surfaces are like the ground floors and the 1st floors of a building, we might be interested in finding out that what will be the relationship between the electric field over that equipotential surface and the potential, which will change, that how it will change. Actually it will change, but we must know that with respect to what it should change. So after this all qualitative agreement, we must go for the quantitative treatment. Some of the mathematical treatments is really required to know the concepts in a better way. So for that, what I am going to do is, I will simply draw the two equipotential surfaces, and then we will see that if a charge is moving from a surface 1 to the surface 2, how and when the things are changing for them. That is, if I got this particular surface like this is, as I promised, is surface 1, and this is my second surface, that is the surface 2. So I have got a charge. So when I place this charge over here, which I denote by plus q, and over this whole area, this charge can move invariably without any effort, no restrictions at all. But if this charge is having a dream to come over to the surface 2, then what will happen? Now, since these surfaces are equipotential surfaces, that means the potential is equal over all these surfaces. That is, it will be same here for this one. It could be a different from the one surface, but it will be same for the second one. Oh, getting a bit confused. Actually, that's my fault, because I just forgot to tell you that what will be the potential there. Say suppose the potential for this one is V, and in the same way the potential for this one will be V plus delta V. Now, in order to bring this charge from here to here, I have to do certain work. What that work will be is nothing but the electric field times the difference in the distance between them. Suppose these two are at a distance which is delta L apart. So what will be the work done? The work done will be nothing but it will be E times, well, why I did that? Because I am only considering the magnitude of it, and it should always be done, because for equipotential surfaces most probably you will get the positive ones as the electric field intensity. So you must take this thing into account quite seriously. E times the delta L will be the work done. So this is E dot delta L. What is this equal to? This is equal to the how much potential a charge has to suffer, or a charge has to undergo change in the potential while moving from 1 to 2. So it is V plus delta V minus the potential here, that is V. So this will give me simply delta V. Now for this delta V, what I have to do is, I will simply say, okay, then what will be the relationship between E and V and L? So it will comes out to be E is equal to delta V times, it is divided by delta L. Well, it is quite comfortable to have this one. Now suppose I have not taken this E to be positive in consideration, but in reality if I don't take this E to be positive, then what will happen is that the E will become the negative of the gradient of it. That is, if I take E to be simply as E, what it will become is, it will simply become minus delta V by delta L. So what have we discussed so far today? We discussed that the continuing from the potential due to a single charge and due to a dipole, just like we did the Coulombic force and the electric field for a system of charges, we can have the electric potential due to a system of charges by simply considering one charge and then integrating it over all the area or the space of my interest. And then we talked about a very unique and beautiful concept of electrostatics. We talked about the equipotential surfaces, which are characterized by the freedom they give to the charges to move over them without spending any energy or the potential. That is, the potential remains same everywhere. Then in the end, we carried out a simple mathematical formulation of what if a charge has got the ability to come from one equipotential surface to this next one, and how much will the each will change. And we find out that E was equal to minus delta V by delta L. Thank you.